The two 10 cm long parallel wires in figure 24.45 are separated by a distance of 5 millimeters. So I have to be careful that we have millimeters here, centimeters there. For what value of the resistor R will the force between the two wires be this? Okay, so whenever we think of forces acting on a charged particle, I think of force equals QE plus QV cross B, where E is magnetic field, or E is the electric field, B is the magnetic field, V is velocity. So we don't have an electric field here, at least it's not mentioned. So we're going to assume that it's, for all intents and purposes, 0. So we're left with QV cross B. Now this isn't a derivation by any means, but just more of a mnemonic. And so you can think of charge is charge, basically the electrons, and V is the speed of the electrons moving through the wire. Now, just for formalities here, we assume that current is positive charges moving the positive direction, when in reality, current is negative charges, electrons, moving the negative direction. Mathematical point of view, both the same. So we're going to take this velocity, which is measured in meters per second. We're going to take that meters per second, we're going to take the second and move it under the charge. And so what we have here is charge per second times length cross B. And charge per second, well, that's just current. Current is measured in amps, and it is charge moving through a wire per second. So we get the formula I, L, B, L cross B, where the direction of L is the direction of the current moving through the wire. So this is the formula we are going to use, F equals I, L cross B. So when we learned this formula in the Navy, based on 12-year-old boy humor, we used the mnemonic fire incinerates little bunnies. Now, granted, a little bit sick, but that's not, a little bit unpleasant, but that's the way little boys work. And like, aha, kind of funny. Focus. F equals I, L cross B. That's the formula we're going to use. This is how I kind of remember it. So that's where we're going to start here. So this wire on the left is going to create a magnetic field, force between the two wires. They just want the force. They don't care about the direction. So current's going to go through here. This current carrying wire right here is going to create a magnetic field. It's going to go this way. And so at this point, it's going to be out of the board. We don't care about the direction, but I'm just showing it anyway. And that magnetic field is going to interact with the current through the wire in the right. And that interaction between the magnetic field and the current is going to create a force. Now these are going to be going in the same, current's going to be going in the same direction. I just know that when you have two current carrying wires carrying current in the same direction, they're going to be attracted. So that's going to create an attraction pulling these two circuits together. So first thing we want to do is we want to find this magnetic field. And so magnetic field is, for a current carrying wire, is mu naught I over 2 pi r. It comes from Ampere's law, and it's just something worth memorizing because you'll probably use it a million times. And in this case, we have a voltage and we have a resistance. So current is going to be Ohm's law, V over R. And so we can rewrite this. Magnetic field created by that wire is going to be mu naught over 2 pi r. And I'm going to use a small r for the distance and the big R for the resistance. So we'll try not to get too confused. V over R. We're told that little r is 5 millimeters, so 5 times 10 to the negative third. We know that big R, resistance, is 2. We know that voltage is 9. Mu naught equals 4 pi times 10 to the negative 7th. And so we can figure out what the magnetic field is going to be due to the left circuit at the point of the right wire. And so this is going to be 4 pi times 10 to the negative 7th times the voltage, which we said was 9. I'm going to check that again, even though I just looked at it. Yep. And that's going to be divided by 2 pi r, which is 5 times 10 to the negative 3rd. That's the distance from the wire, times 2. Yep, 2 ohms. So what we're going to do is we're going to start canceling things. Hopefully lots of things will cancel out. That becomes a 2. That 2 cancels with that. 10 to the negative 3rd on the bottom is the same as 10 to the 3rd up top. 10 to the 3rd and 10 to the 7th is 10 to the negative 4th. And so we have 9/5 times 10 to the negative 4th Teslas. And I'm just going to leave it like that for now. Okay, so we just found the magnetic field for this equation. So we're going to go back to our force equation. We're going to expand it out a little bit more. Current, this current is going to be different than current to the right circuit. It's going to be different than the current of the left circuit, most likely. And that's going to be equal to voltage divided by R. Now they give us this force. So what we effectively want to do is I'm going to rearrange this. We want to solve for the current. So current, this L cross B, a cross product is a measure of how perpendicular two vectors are. And if we do the right-hand rule on this wire coming down, thumb going down, direction of current, wrap your fingers, the magnetic field at this wire is going to be coming out of the page. So magnetic field is coming out of the page, the current in the right wire is going down, those are going to be perpendicular. Therefore, the magnitude of the cross product is going to be the angle between the two vectors, or it's going to be the sine of the angle between the two vectors. Sine of 90 degrees is 1, so we basically just ignore it. So it's going to be force equals IL times B. Rearranging that to find current, we're going to be current equals LB over force. Current is going to be voltage divided by resistance. So it's going to be voltage divided by resistance equals LBF. And so now we're going to work with this. We want to find, I know it's a bit messy, resistance, what resistance R. And so rearranging this, hopefully for the last time, resistance equals voltage times force over length times magnetic field. And this voltage here is the voltage of this battery on the right, which also happens to be the same voltage as the battery on the left. So we're starting to put numbers in here. We're going to have 9 volts times the force between the two wires, which they give us is 5.4 times 10 to the negative 5th, divided by L, which is the length of the two wires, which is 10 centimeters, which I'm going to write as 10 to the negative 1st, because 10 centimeters is 0.1 meters. 0.1 is the same as 10 to the negative 1. I'm just going to write that because hopefully it'll be easier to cancel things later. 9/5 times 10 to the negative 4th is the magnetic field. So I'm going to rewrite this. So we have 9 times 5.4 times 10 to the negative 5th divided by 10 to the negative 1, 10 to the negative 4th becomes 10 to the negative 5th. And I'm going to write this as 9 times 1/5. The 9s cancel out, the 10 to the 5ths cancel out, and we're left with 5.4 divided by 5, which is, can I do that in my head? Feels like it's going to be 1.08 on clear. 5.4 divided by 5, 1.08. 1.08 ohms. So let's take a look back real quick, see if that even makes sense. 5.4, yep, blah, 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 possibly. So to backtrack and kind of look what we did here, we were asked to find the resistance value here that would allow enough current to flow through these two wires, and based on how far apart the wires are, we want to find a certain force, and this is going to be an attractive force because the current and the wires are going parallel, same direction. So we start with the idea of force equals QE plus QV cross B. We quickly simplify that to the force on a current carrying wire, which is force equals IL cross B, where L and B are the directions of the current in the wire, and B is the magnetic field. They happen to be perpendicular, so we just drop the cross product, just L times B, because a cross product is a measure of how perpendicular two vectors are, and when the vectors are perpendicular, then you can drop the cross product because it's the same as multiplying by 1. And from there, it was like, well, okay, so what is B? Well, B is the magnetic field created by the circuit in the left, specifically this wire. So we found the current going through the resistor, which is going to be the current going through that wire. That current then creates the magnetic field. And we want to know what that magnetic field is going to be at the point of the other wire right here, which is 5 millimeters away. That magnetic field then is our B. We then want to find our current going through the right wire, so we know how much it would interact. And we found that using Ohm's law. I equals V over R. Also you can say V equals IR. Both exactly the same, exact same concept. We then plugged everything in, did some algebra, and then came up with the final answer, which was about 1.08 ohms. So I know this one has a lot of concepts involved. The actual problem itself isn't too bad as long as you don't let it confuse you. So I hope that helped. See you on the next one.